Hi, everyone. What do Twitter, power grids, and the human brain have in common? At a fundamental level, I would argue they're all systems made up of many individual elements that, through their interconnectedness, produce some large-scale behavior. They are networks. Now, real-world networks and the dynamics of information spreading and interaction on them can be extremely challenging to analyze. My work as an applied math researcher is to develop innovative mathematical tools to understand these complex systems and make predictions about them. Now, all of this can sound a little abstract, so for most of this talk, let me tell you about one specific application, epidemiology. A widely used mathematical model of infectious diseases is the susceptible infected recover, or SIR, model. Here, the network we consider is a network of people who are connected by their social contacts, like family, friends, co-workers, everyone here in this audience. And every individual is in one of three states: susceptible, infected, or recover, hence the name. A susceptible individual is someone who doesn't have the disease, but they could catch it if they become exposed to it. An infected individual is someone who actively has the disease, and they could spread it to susceptible individuals across network contexts. After some time, they recover. This means they don't have the disease, they cannot be reinfected. They have immunity. Now, as we look at the dynamics of disease spreading over time, we want to ask, well, how big will an outbreak be? This, for realistic networks, is extremely hard to answer because it's hard to track the many ways in which different individuals influence each other. Well, let's put our math hat on and do some thinking. In probability theory, a very useful way to make sense of a complicated system is to appeal to some theorems called laws of large numbers. Here's an example. Say that I ask you to flip a coin 1,000 times. Well, the possible number of outcomes of this experiment is 2 to the 1,000, which is an incredibly large number. It's more than there are stars in the observable universe. And yet, we know that the fraction of heads will be about 1/2, which is the statistical mean of any one coin flip. Now, hiding a lot of technicalities, we can do something similar and understand the global behavior of an outbreak by looking at its local dynamics. So here's a network. Here's a large network. And say I want to know what is the fraction of individuals who are infected at any given time. Think about the fraction of heads from the coin toss example. Well, this, by a certain law of large number, is approximated by randomly choosing one individual and then zooming in, zooming in on that individual and its immediate contact and looking at their statistical properties, like the mean from earlier. It's just like zooming in on a single coin flip. Now, using this theory, which is something called local convergence, I've developed some differential equations that closely track SIR outbreaks on a broad class of random networks. Here's a plot. You can see this red line is my prediction of the fraction of infected individuals over time in an SIR outbreak on a large network. And here, the same quantity obtained through simulations. As you can see, my prediction is pretty spot on. This means that we have a way to know how an outbreak will evolve without needing to run a lot of simulations. And it's also like mathematically exact, or at least like precise. Compared to existing mathematical tools, local convergence has two main advantages. Number one is that existing mathematical tools are only reliable on networks that are extremely dense, meaning there are many, many connections. Local convergence can handle much sparser and thus more realistic networks. Number two, existing tools don't quite see the local connectivity structure of a network. Local convergence does, and therefore it can provide insight into the relationship between local network properties and outbreak size. Finally, let's take a step back from the SIR model. All of these local convergence tools can be used in a plethora of applications to understand global behaviors that arise through local interactions. Through the tools I've been developing in my work, we have a powerful theoretical framework to study networks wherever they arise and gain a better understanding of the interactions among people and neurons and molecules and power stations and computer servers and so on and so forth. The power and beauty of this versatility is why I'm passionate about applied math research and why I hope you think it matters too.